Hello and welcome back, everybody. Today in calculus, we start a new section on this chapter that is on sequence and series. So, back then when you did it in Algebra 2 or pre-calculus, that wasn't the end of it. This is actually a continuation of that. So we're going to look at how does sequence and series apply to calculus and, what are the application by the end of this chapter. So for first, we're going to just go ahead and do kind of like a quick introduction from what we did, I guess, like a couple of years ago. So to begin with, a sequence is just a list of numbers in a definite order. So that means that, you basically just have a string of numbers, and that's going to be a sequence then. Now, does it necessarily have a pattern? The answer is no. Sometimes a sequence doesn't have a pattern, but the ones that we're dealing with does actually have a pattern. So we're going to look at that then. So here, underneath, you can see that we have a sequence then. So you have like the first term, you have the second term, the third term, and so on and so on and so on, where n represents the number of terms, and then we're going to, sorry, out of breath for some reason, where n is supposed to represent the number of terms, so that means that n has to be some sort of an integer value, whole numbers. Now, the notation that you have could be written as like this right here, where a of n is written inside a bracket. Or maybe you have like an a of n inside a bracket, and then you have a notation of n is equal to 1 all the way to infinity, meaning that the sequence goes on forever. So some examples of sequences would be like below over here, where you have this right here notation, where you have the first term, second term, third term, fourth term, and so forth like that. What we can do is with each sequence, we can write it in this form, or you can write it as kind of like a function, if you can see what the equation is going to be then. So here in this case, I think it's actually easy enough for us to be able to do that. So a of n, if I were to call this my sequence, is going to be the following then. The first term, you can see you're trying to look for a pattern that goes from the first term to the second term. Now, some are going to be obvious, some are not going to be obvious. So in this case, hopefully they're going to give you something that is a little bit obvious. The first thing I notice is that the numerators, well, you're basically looking at even numbers. So then that means that you're going to have 2n in the numerator, right, to represent that you're going by even numbers. Then the next thing I notice is the bottom part is kind of like perfect squares, but one more than perfect square, because the bottom over here, you can see that that is going to be 2 squared plus 1. The next one after that is going to be 3 squared plus 1. And then the one after that is going to be 4 squared plus 1, and so on and so on and so on. So in that sense, then that means that we have n plus 1 quantity squared, and then plus 1. And finally, for the alternation of the negative to positive to negative to positive, and so forth, it's going to be multiplied by negative 1 raised to the n power. Okay, so this is something that you kind of like just have to kind of break apart one at a time, just so that you can see what the pattern is going to be then. Okay, now underneath right here, that's another example of a sequence. This one is actually written in a form that might not be familiar, but you can kind of like work backward to see exactly what's happening. Here, they tell you what's the first term and the second term, so you can kind of write that out. So the first term is 1, the second term is 1. Now here, they give you a formula to figure out what's the third term and fourth term and so forth. So if I were to say n is equal to 3, then that means that f of 3 is equal to f of 1 plus f of 2, or actually f of 2 plus f of 1. So f of 3 is equal to the sum of the two previous term, which would be 1 plus 1. So the answer is equal to 2. So that's going to go here. Then f of 4, where n is equal to 4, is going to be f of 3 plus f of 2. So it's going to be the sum of the two previous term. So then that means that it's going to be 1 plus 2, so that's equal to 3. So that goes over here. And if you were to follow this equation every single time, the next one is going to be 5, because it's 2 plus 3, which is equal to 5. Then the next one after that, it's 3 plus 5, which is equal to 8. And so on and so on and so on. And so you can probably see now that this is the Fibonacci sequence that you've been told about a very long time ago. So in short, what's happening is that whenever you're given a sequence is usually going to be some sort of function where the domain is going to be a subset of integers, mainly again because you're counting which term you actually have in this case. Okay, and therefore we can apply everything that we learned about functions so long as we're looking at the domain as integer values. And in this case, that means that limits, we can go ahead and apply to this one also as well. Okay, so here are some problems that you're going to run into then. So here what I want to do is determine if the following is going to be convergent or divergent, okay? So I'm going to give you a sequence, which again, you can treat it as like, say, a function. And I want to know if the number that it's approaching to is going to be something then. Well, since we can approach it using using a function, or think of it exactly the same way, we can go ahead and apply all that to it then. So looking at the very first example over here, I want to find the limit as n approaches towards infinity of 4 times n squared divided by 7 times n squared plus 3n minus 1. So we can go ahead and using two ways. We can either, number one, if you remember the rule, was to divide both top and bottom by the greatest monomial in each part, or from the whole thing. So that's dividing everything by n squared. And then as a result, you're going to then get a limit as n approaches towards infinity of 4 divided by 7 plus 3 over n minus 1 over n squared. And if we apply the limit once again to n, for everywhere we see n, you're going to see that any term that contains n in there is going to go to 0. So as a result, you get 4 over 7 plus 0 minus 0. So the answer is equal to 4/7. The quick way of seeing this is that if you have the polynomials that are of the same degrees, then that means that as n approaches towards infinity, it's most likely going to go to their coefficients then. Okay. The next one over here on the right-hand side of it, limit as n approaches towards infinity of ln of n divided by n. Well, this one, unfortunately, is not as obvious, but it is one of the limits that we have done before in the past. So one thing we can do is just think about, okay, well, if we don't know what the limit is, or we can't see what to do algebraically, always try to plug it in to see what happens then. So limit as n approaches towards infinity of ln of n over n, that is going to give you infinity. Whereas limit as n approaches towards infinity of n, just the denominator, that is also going towards infinity. So that right there is what we have called the indeterminate form, because we have infinity over infinity. So that means that we can go ahead and use L'Hopital's rule, indeterminate form. Okay, so form right there. So by L'Hopital's rule, we can say the limit as n approaches towards infinity is going to be the derivative of the top, which is 1 over n, divided by the derivative of the bottom, which is going to be 1. And now, once again, we're going to go ahead and apply the limit. So as n approaches towards infinity, then that is going to give me 1 over infinity, and that means that it's going towards 0 then. So anytime that you have a limit and the limit is equal to 0, then that is what we call convergent. And it's most likely they were going to ask you to do both. They want you to find out if it's convergent, and if it is, what does it converge to? But whereas if it diverges, then you're pretty much done as long as you show it diverges. Okay, next one over here. What is the limit as n approaches towards infinity of 1 plus 1 over n to the power of n squared to the power of n? Well, this one, you can apply L'Hopital's rule again, but it's one of those where I'm hoping that you've actually memorized, because it's going to come up quite often. This right here, this is applying to, this is basically applying the following limit then. If you have the limit as n approaches towards infinity of 1 plus a over n raised to the power of b times n, the result is that the limit is equal to e to the power of b multiplied by a. So this is going to be where a is equal to 1 and b is equal to 1 also. So the answer is supposed to be e to the power of 1 times 1, so the answer is equal to e. In terms of where the proof is of all of this, well, here I can I guess leave it over here and you guys can kind of take a look at it. But it was proved back in chapter 3, where you're supposed to take the ln of both sides and then apply L'Hopital's rule to see that the result is what I just told you right there. So it's not something that's just like, black magic or whatever. Okay. All right. And then here's another last one, which you can also apply using the limit laws that we have. In this one, we have cosine on top, and then we have n on the bottom. We have a slight problem here, because as we apply n is approaching towards infinity, the numerator is going to be inconsistent because you're always fluctuating between -1 and 1 because that's what cosine is as a result. So that could be problematic. But if you do remember from the very, very beginning, there was a limit law called the Squeeze Theorem that we can apply. Because of this situation right here in the numerator, then what I can do is apply the following. We're going to take this inequality and then divide everything by n, and now apply the limit to each part. So limit as n approaches towards infinity of this part is equal to, or so less than or equal to, the limit as n approaches towards the infinity of the inside is less than or equal to the limit as n approaches towards infinity of the right side. Both the left hand and the right hand, the limit is equal to 0 because n is in the denominator. So because you have an upper bound that is going to be 0 and the lower bound, which is going to be equal to 0, then by the Squeeze Theorem, then we can say that the limit as n approaches towards infinity of cosine of pi times n over n is going to be equal to 0 then. Okay. So again, all of those limits law that you have remembered and hopefully haven't forgotten, you can definitely apply in this case because a sequence is really just, again, a function then, okay? So here are a few more examples, which I need to scroll up and then scroll back down because my screen is kind of messed up over here. Well, I guess it's not showing up then. There we go, much better. So here, I wrote down the Squeeze Theorem just in case you forgot. And here, underneath it, there is something called, or I guess there's no name for it, but this is called, I guess, Theorem Number 6 in this case. It says that if you have the limit as n approaches towards infinity of an absolute value of n, absolute value of a of n is equal to 0, meaning that if you take the absolute value of a sequence and then you find the limit of it and it turns out to be equal to 0, then that means that the limit as the sequence itself goes to infinity is also going to be equal to 0. The way you can prove that, Theorem 6, is by using the Squeeze Theorem, where the above function is a of n and the below function is going to be b of n. And so as a result, then yes, it should equal to 0 then. So we'll see how to apply that right here in a little bit more, okay? So what I want to do now is I want to go ahead and introduce like some problems with limits that, well, it's a little bit different than the ones that we did in the past, okay? So here in the first one, you can see that the limit as n approaches towards infinity of 4 to the n divided by 1 plus 9 to the n. This unfortunately is a little bit harder to see as to what the limit is because even if it does converge, we need to figure out what the number is. Well, back in chapter 7, not too long ago, we had something called comparison test, which says that if you have a limit, actually, let me kind of rewrite it over here. If you have two sequences where one is always going to be below the other, and it's the case where the upper limit as it goes to infinity is supposed to be convergent, meaning that it has a finite term, finite sum of this, then the result is that the lower sequence, as it approaches towards infinity, is also going to be convergent then. Okay, so if I can find an upper function, which is, or I guess in this case, if I can find an upper sequence that is going to be convergent, then therefore this is going to be therefore this is going to be convergent. Well, the part that's problematic is actually just this one over here because, well, I just don't like it. So what we can do is we can say, hey, let's compare to something that we know it's going to most likely be convergent to. And that thing that we have to compare to, or we should compare it to, is the following. The limit as n approaches towards infinity of 4 to the n divided by 9 to the n. That right there is something really nice and clean, and we know what the limit is going to be. So in this case, because we compared it to this right here, and we know that this is true because the denominator is always going to be smaller than the denominator on the left-hand side, then now we can go ahead and find the limit of this one. So this guy right here, this we can go ahead and simplify. This is going to be the same thing as limit as n approaches towards infinity of 4 over 9 raised to the nth power. And if you look at what we have as an exponential, kind of like an exponential function, the inside the base is less than 1. So therefore, this has to go to 0, because if you take 4 to the ninth, 4 over 9, and keep raising it to some exponent, any number that you take between 0 to 1 or -1 to 1, and you raise it to like an infinite exponent, the result is that it's going to get smaller and smaller and smaller. So therefore, by the comparison test, then that means that what we're trying to solve for right here is going to be convergent. So by comparison test, the limit as n approaches towards infinity of 4 to the n divided by 1 plus 9 to the n is going to be is convergent. Now, in terms of what it converges to, that's where it's a little bit trickier, because the upper bound converges to some number that we know supposedly, but then the lower bound might not converge to that same number. It could converge to something that's a little bit smaller than that. And what it converges to, we actually don't know. In some cases we know, in some cases we don't know, but in this cases, you get an idea that it's going to be the same thing as what's above it. But if it's a little bit more complex, then we can't actually be conclusive, and therefore we just say it's convergent then. The next example over here is that we have limit as n approaches towards infinity of -1 to the n divided by n. Now this one, this is basically utilizing theorem number 6 over here. We are going to look at what happens if we take the absolute value of it, because the indication is this alternating sign that goes from -1 raised to the n power. If we were to write it out, here's what it looks like. This is basically going to be -1, and then we have 1/2, and then -1/3, and then we have 1/4, -1/5, 1/6, and so on and so on and so on. So if you can see it, the whole thing, the sequence as a whole is getting smaller and smaller and smaller. And if you were to just get rid of the absolute value, it's going to be the same thing. So here, what we can say is, since, or actually here, let's kind of like start from the top. We can say let a of n be equal to -1 raised to the nth power divided by n. Then a of n, the absolute value, is equal to 1 over n. And limit as n approaches towards infinity of absolute value of a of n is equal to 0. Therefore, by theorem 6, then that means that the limit as n approaches towards infinity of -1 to the n divided by n is going to be equal to 0 then. Okay. All right. A couple more over here. These ones, again, it's a little bit more complex than the ones that we've been doing so far, so just kind of bear with me over here. This time I want to find the limit as n approaches towards infinity of n factorial divided by n to the nth power. Well, this one, any time that you don't know where to go, because, well, for one thing, we don't know where to go because of the factorial sign. We've never really kind of dealt with anything in terms of calculus or limits that has the factorial sign. So anytime that something like this happens, the best thing you can do is actually just write out a few terms just to see exactly what's happening then. So here, let me kind of write it out. For n is equal to 1, we're going to get 1 factorial over 1, so that is just equal to 1, so plain and simple. N is equal to 2, you're going to get 2 factorial divided by 2 to the second power. So if you write that out, that's 2 times 1 divided by 2 times 2. N is equal to 3, you're going to get 3 factorial divided by 3 to the third power. That's 3 times 2 times 1 divided by 3 times 3 times 3. And so notice at each time when I'm writing this out, I'm not writing out the simplified answer for each one because I want to see if there's a pattern that's being generated here. Then we have n is equal to 4. Then you're going to get 4 factorial over 4 to the 4th. And that's going to give us 4 times 3 times 2 times 1. And then that's divided by 4 times 4 times 4 times 4. Okay, so you can now see exactly what's happening. The result is that you're going to get a numerator that is always going to be smaller than the denominator. Okay, you're going to get a numerator that's always going to be smaller than the denominator. So if you were to look at this as it approaches towards infinity, then you can say that the numerator is always going to be smaller than the denominator. So as a result, then that means that you're going to have something that is going to be less than 1. But in terms of what it converges to, well, that's where it's a little bit tricky because we don't know exactly where to go with it. Well, that's where you're probably going to have to do a little bit of algebra to dig in a little bit. So for right now, I'm just going to go ahead and say that it's inconclusive, and then I'm going to let you try to figure that out a little bit, okay? All right. Now here's the last one, which is actually, I think, kind of like an interesting one. Limit as n approaches towards infinity of -1 to the nth power. If we were to write this out again, because we don't know what that looks like, this is basically the following. You have -1 and then 1, -1 and then 1, and then -1 and 1, and so on and so on and so on. That right there is going to be considered as divergent. And the reason is there is no way to know when the oscillation is going to end. We just know that it's going to be either 1 or -1. It doesn't tell us where to stop. So therefore, it's kind of like, sine and cosine, right? As you approach towards infinity, you don't know where the oscillation is going to end. So therefore, there's no conclusive evidence that it's going to be convergent. And convergent usually means that it's going to go towards a specific finite number, not two numbers or something like that. Okay. All right. Well, there you go. Thank you so much for watching. I know this one's a little bit lengthier, and hopefully you were able to bear with me for this one. I'll talk to you next time. Bye-bye.